of the quarter. We're very pleased to have here Hunter Spink, who didn't write his name, but he's writing it right now. And he'll tell us about the anti-concentration of random walks, all definable sets, and welcome.
Okay, so thank you for inviting me to give this talk. Today, I know a lot of you are combinatorialists and some of you are model theorists, and hopefully I can say something to everyone and everyone will be happy, but we'll see how that goes. So this work is on anti-concentration of random walks in definable sets. So first I want to set up my model of a random walk. So let's say we have vectors v1 through vn inside Euclidean space, and we're going to assume that they're non-zero. I'm going to take uniformly random signs. So I'm going to take n signs uniformly random, so all 2 to the n possibilities are equally likely. And from these fixed vectors and these random signs, we're going to make a model of a random walk. We're going to call the random walk x, and it's going to work as follows. We start with the first vector, and we either walk forward or backwards in that direction. So epsilon1 v1, and then from where we are, we then in the direction v2 either walk forward or backwards. Epsilon2 v2, all the way to epsilon n vn. So there are 2 to the n possible places you can end up, and some of them might overlap with each other. This is like a generic model of a random walk, which is non-adaptive. So the next step you take can't depend on the previous steps. It's determined right at the beginning. Okay, so these types of non-adaptive random walks have been very well studied ever since Lilwood and Offord posed their rather famous family of problems sometime in the 30s. So they were studying roots of random polynomials, and they had a question which was later generalized and generalized and generalized. And I guess the most general meta question you can ask is, suppose we have a region of space. So we have a region S in Euclidean space. What is the best possible upper bound? Best possible upper bound and on the probability that x lies in this region with a bracket, which is independent of the choice of vectors. So you want like an a priori upper bound that works for all models of random walks you want to do. And having such an upper bound on the probability that you land in this region is very useful, because if you have this bound, you can just automatically apply it without actually studying the intricacies of like how your random walk is defined. And this is called an anti-concentration inequality, an upper bound to this, because the probability that x is in S is the probability of concentrating in S. So the idea is that we want to show that this is very small, so this is going to be an anti-concentration inequality. So let's see what people have done since the 30s. Lots of work has been done on this problem, including by Terence Tao, who is not here, but he has some very impressive applications of this. But let me just tell you the classical theory. So if you think of a region of space, what is a region of space? A region of space is like a voluminous, and volumes, they contain balls and are contained in balls. So basically the universal region that is of interest would be a ball of radius r centered at some point x. So we have this, we want to know the probability of concentrating in this ball. And for technical reasons that I'll get to in a moment, all previous work has assumed that all of these vectors have magnitude at least 1. And we'll see why this is imposed in a moment. So since Lilwood and Offord asked this question in some form in the 30s, people got better and better bounds in this particular setup. First, Erdős got the best upper bound when d is 1. Then Kleitman found the best upper bound for arbitrary d. And then Frankel and Ferretti optimized some constants in the in this. So they optimized constants. In what inequality? Well, the inequality they optimized it in is that the probability of concentrating inside this ball is big O, depending on the dimension of the space you're in and the radius of the ball, of n to the -1/2. So let's look at this inequality for a moment just qualitatively. So ignoring the specific fact this n to the minus 1/2, what does it mean that the right-hand side of this inequality goes to 0? So to be clear for people that don't do probability, equals big O of this means that the left-hand side is less than or equal to a constant depending on d and r of the right-hand side. So I write equals instead of less than or equal, but I have this big O, so that's the convention. Okay, so what does this mean? Well, the right-hand side going to 0 means it doesn't matter what my model of a random walk is, the random walk is forced to disperse. So if I am like sitting at the origin and I consider the ball of radius 1,000 around myself, and I take 1,000,000,000,000 steps, then no matter how I try and cleverly choose these steps, I'm always going to be forced to leave this ball centered around the origin of radius 1,000, and with a pretty high probability. So it's actually very surprising that there exists any type of bound that goes to 0 and then goes to infinity. But they proved it, and this is a very nice result. Now, what is this n to the minus 1/2? So this is what I want to focus on now. Well, this comes from the best possible strategy. So the strategy in the sense of like what choice of vectors makes me the most likely to get inside this ball and then stay in the ball forever. I mean, get inside the ball and then, after walking around a bed, you end up in the ball. So the n to the minus 1/2 comes from, so the construction, so here's 0, here's the ball of radius r around x. And the first step of the random walk, we're going to take to be v1 to be x. We're going to bring ourselves right to the center of the ball. And there's a 50% chance you succeed and a 50% chance you fail. So you might end up with minus v1. And if you fail, you just give up. You're like, oh, well, I lost a factor of 1/2, but who cares? So conditioned on you succeeding, how am I going to choose the rest of these steps? Well, it turns out that the optimal strategy in general is to choose some fixed vector v and do a one-dimensional random walk in this direction. So once I'm at x, assuming that I succeeded in the first coin flip, I just walk, forward, forward, backwards, 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 forward, forward, backwards, and I really, really hope I end up exactly back to where I start, or within like a bounded number of steps from where I start. So let's estimate what this probability is that I get back to where I start. So let's say for parity reasons, let's say n is odd. In order to end up right back to where I start, I need 1/2 of these signs to be positive. I need 1/2 of these signs to be negative. So I can just count this. So if this happens, then you'll end up right back at x. Well, it won't matter. So if n is odd, v2 through v, what vector you take won't matter because I'm going to look at the probability you end up exactly back to where you start. Right. This is why I'm assuming that vi is at least 1, and we'll see that in a moment. Yeah. So this is important because of exactly what Suyon just said. So okay. So if we take a vector of non-negligible size and we do this, there's n minus 1, choose n minus 1 over 2 successes, and 2 to the n failures, taking into this first coin flip into account. And this is approximately n to the minus 1/2. By Stirling's formula. So this n to the minus 1/2 is just the probability of hitting the median of a binomial distribution on n steps. So that's where the n to the minus 1/2 comes from, one-dimensional walk. And Frankel and Ferretti showed that asymptotically this is the best strategy you can possibly do with some like slight modifications. But this is basically the best possible thing you can do. So this is good. So people know the best result and people are happy. And so young like me, didn't realize that there was this hypothesis that the magnitudes of these vectors are at least 1. So, I saw this and it was like, fine. And I wanted to know, so question, why did we impose this lower bound on the sizes of the v? Yes. The optimal probability, if there's a slight modification of the strategy which changes with d. So Frankel and Ferretti found a slight modification of this which makes it better or worse. Okay, but yeah, so the question is, why do we impose this restriction? So let me rewrite Sui Hong's example to show that it was a really, really important restriction. So I'm literally just going to say what Sui Hong said again. So we take S to be this ball, and we've now dropped this restriction. So now we're dropping this restriction. So we're going to drop the restriction in everything that I'm saying now. So when S is a ball, Sui Hong is absolutely right. If I start at 0 and I have my ball of radius x around x of radius r, take your first vector, bring yourself right into the center of the ball, then you take v2 through vn to be tiny. So if v2 through vn are really tiny, then obviously it doesn't matter what their signs are, you're going to stay inside the ball. The probability is at least 1/2, which is very sad because we wanted, for this type of problem, we want something that goes to 0. Like this means there's no non-trivial inequality we can say, because you can do the stupid trick where you just take all these v's to be very tiny. So let's really refine what the issue with this example is. If S contains a line segment, then exactly the same problem happens. You go 0 to the midpoint of the line segment with v1. You take all these other vectors to be tiny in the direction of the line segment. And then again, the probability that x is an S is at least 1/2. So again, we're sad. Okay, so at this point, we've done 2 sanity checks. And at this point, probably you should give up. But if we don't give up, you say, okay, well, if I want to prove any result about arbitrary random walks, I can't have a region of full dimension because it can't contain a ball. So it has to be a lower dimensional region. And it can't be particularly flat anywhere. So it has to be kind of like a wavy kind of region, like maybe like a surface. But it can't be too wavy because you would also have a problem with the graph of y equals cosine of x. So what's the strategy if you have this periodic thing? Well, here's 0. How am I going to get all the vectors to stay on y equals cosine of x? Anyone? Yeah, okay, everyone's pointing, so it's kind of obvious. All right, so one vector gets you onto the graph. Maybe I should get myself right to the beginning of the period. Yeah. Here's v1, and then the rest of the vectors are going to be in the period. So again, we're sad. So this periodic structure means probability that x is an S is at least 1/2. Okay. So like, what are the odds that we can find hypotheses that like somehow manage to exclude all of these like crazy things that can happen? You know, maybe there are like a lot of other examples. Who knows? So yeah, sanity check. This was a very important hypothesis. But what if we really wanted a positive result? What shapes can we say anything for? Well, one shape you can say something for is S being a single point. Then I claim that the probability that x is an S is big O of n to the minus 1/2. So not very exciting. This actually follows from the ball case because this restriction on the VI being at have magnitude at least 1 is really saying that the VI have magnitude bounded below by a constant multiple of the radius of the ball. So if I see my vectors, I can take a really, really, really tiny ball around my point and apply that result. So it's a little bit more disappointing than that because actually this isn't a higher dimensional result, because if I have some collection of vectors that I thought I was very clever with and concentrated very highly on some point, if I generically project everything down to the real line, all of the concentration probabilities stay the same. So really, this is just the one-dimensional result implies the d-dimensional result, and the one-dimensional result as a cute proof by Erdős. But it's not anything about the geometry of space, just like, you know, a torsion-free abelian group. So this is, you know, this is a good positive result, but, you know, it doesn't help us at all. And I guess you can also do it if S is a finite union of points. So if S is k points, then the probability that x is an S is going to again be still be k times O of n to the minus 1/2. I could put this k inside the O, but I want to point out that as the number of points increases, this constant genuinely goes up linearly with k. It goes 1, 2, 3, 4, 5, as you have 1 point, 2 point, 3 point, 4 point, or 5 points as landing points. So with this in mind, obviously, if I have any infinite number of points, this constant is just going to be infinite and I'm going to fail. But that's not true, surprisingly, because Kevin Costello, as he was working on a project which eventually led him and Tao and Vu to get like the first non-trivial estimates on the probability that certain random matrices were singular, certain matrix ensembles. He came up with the following statement that he needed in the proof, and he proved it using some complicated method, which was if S is a parabola, then the probability that X is an S is, after refining the argument used in the paper, is O of n to the minus 1/2. What a surprising result. Because this is saying, so I have my parabola. Let's start adding landing points for this random walk from this parabola. So I add my first point, I have some constant times n to the minus 1/2. I add another landing point, I have twice the constant, then 3 times the constant, 4 times the constant. But then as you start adding points, eventually this constant doesn't increase linearly, it eventually stabilizes. So you add 5 points, 6 points, 7 points, 8 points. The added value of these new points isn't actually getting this constant bigger. And in fact, this constant is about the constant for like 10 points. It's not a crazy constant here. So concentrating on this uncountable parabola, something about the geometry of the shape means that concentrating on a parabola is no worse than concentrating on 10 points. So, I was very interested in this, and with Jacob and Matthew, we looked at this, and we wanted to know how, like what shapes can we get, this kind of result for? What can we get a positive result for? We get a parabola, what else? So, theorem. Let S in R to the D be a subset not containing a line segment, containing a line segment. So that's important because of the, that problem of the form S equals S phi. So there's going to be some parameter phi, and this parameter phi xd, so it's going to be the set of all d tuples such that phi is true. So phi is actually going to be a mathematical statement, and it's going to be the set of all d tuples of points where the mathematical statement is true, such as y equals x squared. And now I have to tell you what restrictions are on the mathematical statement, where phi is allowed the following things. Okay, so we want to write down, some allowed things for the statement, and want to include, for example, y equals x squared. So the first obvious thing is we're going to need like variables, real numbers, and boring things like brackets. So far, I'm allowing you to write down x, open bracket 3, close bracket y. Not a very interesting thing. So let's give you some operations to combine them to make things so you can write down something like y equals x squared. So I want to be able to write down linear things, so I'll give you plus. You can now write down like 2x plus 3y. And I'll give you times. So you can now write down polynomials. Okay, so I can write down a polynomial. I don't have anything that evaluates true or false yet, but I can write down a polynomial. And I'll just throw in some extra things for you because I want to make your life easy. X, you want to use x, that's fine. I'm not going to stop you. Log is fine. I'll give you any analytic function in R variables restricted to a compact set. Analytic. So I'm being very sneaky with my choice here because I don't want you to write down y equals cosine of x, but I'll allow you cosine of x restricted to any lobe. The individual lobes aren't the problem, it's the infinite periodicity of it. So you can include all these, and you can make rather complicated functions, and these functions don't exhibit this kind of periodicity. But okay, a function isn't true or false, so we need predicates to make it true or false. So less than equals greater, go for it. So now we have subsets of space defined by equality, inequality, and an inequality of something of this form. And you might want to have multiple equalities and inequalities. So I'll give you all the standard and, not, or, implies by implies. I'm not cleverly excluding anything here. Any logical connective is fine. And then finally, although it doesn't increase the expressive power particularly, like the amount of sets that with this next thing will allow you, doesn't increase it that much, but it's very handy to have. I'm going to allow you to quantify over the real numbers. So you can go, there exists x, and you can go, there's for all y. So for example, you can now talk about the place where a function is continuous or differentiable, because the calculus textbook definition of continuity and differentiability is for all epsilon there exists a delta such that yada, yada, yada. So with this, you can, for example, talk about the region where something is continuous or differentiable. Okay, so these are the things that are allowed. And assuming you have a formula that, that meets this criterion, then the probability that x is an S is the following. When d equals 2, we have the optimal bound. So in particular, a parabola as a special case. And when d is at least 3, we could only get n to the minus 1/2 plus little o s of 1. So this exponent approaches negative 1/2 as n goes to infinity. So it gets closer and closer and closer. It's a little bit weaker than having the constant in front of it. And we actually conjecture that this is the optimal thing in general. The only thing that's really stopping us is we would have to prove the corrected Gaussian lineal conjecture for Boolean functions, and we'd have to obtain optimal counts for rational and algebraic points of bounded height on transcendental surfaces in O-minimal geometry, and we can't do either of those. So this is, this is what we got. I mean, you have to give up at some point. Great. Okay, so how would you prove something about these kinds of sets? Well, first I'm just going to talk about how to prove any upper bound on the probability that x is an S for just like any subset of space. Like what structure of a subset of space would be useful to have to allow you to get a non-trivial upper bound on this. So let me make a definition, which is essentially the structure that we end up showing that sets of this form have. So say S is of, I'm going to put dimension in quotes, so it's not geometric dimension. This is quote dimension. Dimension K of complexity C. So I'm going to have a parameter C in my definition of dimension if the following is true. The following is true. So this is going to be an inductive definition. When K equals 0, dimension 0 sets are sets with at most C points. Okay. So complexity is controlling the number of points at the base. If K is bigger than 0, then my requirement is that I can take S, I can break it up into pieces. I can, in fact, break it up into C pieces. And each of these pieces has the following property, that if I take two distinct translates of the piece and I intersect them, then this is one dimension lower of complexity C. Okay, when Z is not equal to. So this is kind of the fundamental structure that I claim that these sets have, which is going to allow us to prove upper bounds like this. Now, what is the motivation for this definition? Well, let me say what this definition says when C is equal to 1, and then it'll motivate like what I'm doing over here. So when C is equal to 1, this structure is saying S does not contain the vertices of a possibly degenerate K plus 1 dimensional parallelepiped. or equivalently, the sum of k plus 1 two-element sets. This is like the discrete version of a zonotope. So when C is 1, this is a reasonable first way you could possibly imagine to define the dimension of a subset of space, given only its additive structure. So I have this like subset of space, and it lies inside R to the D. Now let's say I just forget that R to the D is this Euclidean amazing thing. I literally just have a subset of an abelian group. How am I going to figure out what the dimension was? Well, this is a reasonable way of assigning a dimension, because it says, you know, they're naturally k plus 1 dimensional things from an additive perspective. And you might say, well, if you don't contain a k plus 1 dimensional thing, then you're k dimensional. Fine. However, that runs into a problem that this is not stable under unions. So I can create sets which pretend to be high dimensional, even though they're very low dimensional. For example, if I take 4 points in the shape of a parallelogram, like if S is literally this collection of 4 points, I don't want to assign that dimension 2, I want to assign a dimension 0. So this definition fixes that problem by forcing this definition to be stable under unions. They claim this is a reasonable definition to have, because in fact, the key structural theorem that we prove about these sets defined in this way is that if the Euclidean dimension of S, so the Euclidean dimension of S equal to K, then we show that there exists a C such that S is dim K of complexity. Okay. Oh.
So you
Sure.
have a theory. Definition as a part of the proof?
No.
Or you're trying to explain the theory?
I'm going to explain various aspects of this theorem. This theorem is here. And now here's a definition that's important to me. And I'll prove something about this definition.
Okay.
Yes, but these sets are like naturally going to be like unions of manifolds, so we'll have a dimension. I put it up here. Sure. This is the cardinality. So when K is 0, I want a dimension 0 set to be a finite union of points that the size of the union is C. Well, so with this definition of dimension, actually balls and line segments are going to have infinite dimension, because it turns out that it's not possible to do this type of decomposition. And you can't really do this type of decomposition for an infinite arithmetic progression. It's a consequence of van der Waerden's theorem that basically like subsets of arithmetic progressions always contain arithmetic progressions. So you can't like break it up in a way so that when I intersect it with the translate, it actually loses structure. The line segment's bad, and yeah, that's, yeah. Well, that will be after I tell you what the actual thing that should be here that's more general than that is. And that's what the model theorists have. So I'll tell you that in a moment. That would also be fine, but you can just increase the constant C to make that happen. Yeah. So this constant C kind of fixes all problems of, this constant C basically makes it so if I have this subset of space, there's like finitely many times when one part of it is isometric to another part. And this just like shatters your set in such a way that you never have one part exactly isometric to another part. So it fixes all those problems. No, so this definition is a definition for any, so this definition is for any subset S of r to the d. You say it's of this dimension if this happens. And then the fact is, if the Euclidean dimension of a set like that is k, and it doesn't contain a line segment, so any s that this theorem applies to, so one of these s phi's, if one of these s phi's, as in the theorem, has dimension k, then there exists a constant so that it has the corresponding additive notion of dimension. Yes, because this notion of dimension is only the dimension, this notion of dimension doesn't use anything about the Euclidean structure of the space. It's only what the discrete, what the abelian group structure can see. So from that perspective, anything like an arithmetic progression that goes on forever is going to cause, you can't assign a dimension in a consistent way to those things. So this does not apply to a ball because balls contain line segments. So you have to have a lower dimensional subset of space for this to apply. Yeah. So we use O-minimality to prove this. And then we use O-minimality we use the Pila-Wilke point counting theorem to improve the result I'm going to state all the way to -1/2 plus a little of 1. So we're going to be used 2 times, but I won't talk about the second time. He asked, where's O-minimality going to be used? I haven't said the word O-minimal yet, but it'll be used in, well, I'm not going to say how it's used in the proof of this fact, and I'm not going to say how it's used here, but it's used in 2 separate places in an important way. Because, yeah. Any other questions? No, the finiteness of this dimension will give the same result with 2 to the k plus 1. And then you will need to use the Pila-Wilke point counting O-minimality to get beyond. So Artem wanted to know if this fact was all I was going to use to prove this theorem. And the answer is no. This fact can be used to prove this theorem with 2 to the k plus 1 in the exponent. If you want to improve it to 2, you actually need to use the model theory again. And that was rather surprising that we used model theory first for this, and then we lucked out, and someone proved something useful in model theory in a different context, which was again useful, and then it just worked out really. Any other questions? Okay. Right. Okay. So what I'm going to do now is I'm going to do combinatorics, and I'm going to tell you something about model theory. So the combinatorics, so here's a claim I'm going to prove. If S, so this is related to Arten's question, if S is of dimension k and complexity c, then probability that x lies in S is big O, depending on k and c, of n to the -1 over 2 to the k plus 1. So this is a worse thing than what the theorem guarantees, but I only need to use this like recursive thing. And this is actually has a really, really elementary combinatorial proof. So I'm going to do the proof for c equals 1, because basically for a larger c, you just apply the union bound at the start to your set. So what c is 1 is where the magic is contained. Okay, so what are we going to do? I'm going to need a probabilistic lemma, which I'm going to call the decoupling lemma. So the sub-lemma. The probabilistic inequality says the following thing. Suppose I have some event that depends on 2 random variables. So this is an event, and y and z are independent random variables. And so this event might be true or false. I get y, I get z, I see if the event is true. So suppose I don't like, I look at this and I'm like, I didn't like z. So I'm going to resample z. So z prime, the resampled independent z. See? Then we have the following inequality. Probability of this event occurring is at most the probability of the event occurring and the event occurring after resampling the second part, the 1/2. So this is a correlation estimate because this event and this event have the same probability. They have probability of this event. And this says that this event and this event are positively correlated. So if I take any event that depends on two things, they resample the second thing, there's a positive correlation. If one is true, the other is more likely to be true. If one is false, the other is more likely to be false. Okay, so given this, we're now in a position to prove the theorem. So here's what we're going to do. So I want to estimate the probability that x is an S. But x is a single variable and I need two variables. So the first step is to take this x and split it up into two parts. So this is the sum from 1 to n. We're going to split it up into the first half of the steps and then the second half of the plus. The random walk is made up of two parts. And now this event that x lies in S can now be written as an event which depends on two independent things. Is that y plus z lies in S. Okay, so the probability that x lies in S is equal to the probability that y plus z lies in S. And now I can apply this lemma, say this is less than or equal to the probability that both y plus z and y plus z prime are in S. Let me draw a picture of this. So if I have my random walk, so it goes up to y to z, I guess there should be a 1/2 over here. So we're trying to estimate this probability that the random walk ends up in here. And I'm saying it's easier to estimate the probability that this happens when I resample the second part of the random walk, so that both of these branches end up lying in S. Now here comes the fun part. This is the same as the probability that y lies inside the following random subset of space. S minus z, that covers the first condition, cap S minus z prime. Okay, so y lying in here is the same as this sum condition, and y lying in here is this sum condition, and intersecting them forces both conditions. So this is the same as y lying in this intersected set. And this has dimension k minus 1 by definition, so you induct. And the base case of k equals 0 is like S is a single point, so it follows from the single point thing I wrote over there. Okay, so yeah, you just induct with this statement, because this is a random walk of length n over 2, and this is something we can apply the induction hypothesis to. And that's all I'll say about combinatorics. Any questions about that? Good. Okay. So now there was a lot of questions. The rest of this is going to be short, but is it okay if I? Okay. So now I want to tell you what's special about this collection of functions. This is where the model theory comes in. I want to give everyone their first model theory proof, because I feel like I didn't know any model theory. And then, you know, at some point I knew model theory, and at some point there was the first proof. So I want to tell you the first proof. Okay, so let's give a definition that tells you what's special about this collection of functions. So a collection of functions such as star is said to be O minimal if for all d and for all formulas, just like in the theorem statement, I'm not going to repeat all those other things other than what that star was. This set, defined using phi, as in the theorem, has finitely many connected components. Many connected components. Which seems like a really weak and confusing definition. But the model theorists are very clever, and it turns out this definition has the highest output to theorem input you could possibly give. And that this looks like a silly definition where you can prove anything, but it turns out that you can get amazing things from this definition. For example, you can show that if you have a collection of functions that satisfies this hypothesis, then every set of this form is a finite union of manifolds. So no Cantor-like set things can occur as a result of this definition. You always get everything is like, 10 times differentiable union of manifolds. So these manifolds are also differentiable to whatever order you want, which is surprising. And now let's talk about, sorry, what was your name? The person who asked, why is cosine of x not definable? Yes. Jacob? Okay. So Jacob asked, what about cosine of x? So let's use this definition to show that cosine of x would be a bad thing to include in an O-minimal collection. So let's create a function. I'll do it of two variables. And let's try and create something that has infinitely many connected components. So let's just try y equals cosine of x. Does that work to show cosine of x can't be included? No, because it has only one connected component. So as of this point, I haven't ruled out the graph of y equals cosine of x being one of these fancy sets. But I can use it in a further formula by modifying this formula and saying, and y is equal to 1. Now, by using cosine of x in this formula, we now get all multiples of 2 pi and 1, which is infinite. So this definition, the subtlety, if you want to think of the definition as a restriction on the sets themselves, was really saying is that the set has finally made connected components, fine, but also if you use it in any crazy geometric construction that you could possibly imagine, like anyone at all, you'll always have finitely made connected components. It's a universal guarantee you'll never end up with infinitely made connected components. And I guess with that in mind, it's quite surprising you can get such a large collection of functions to make that work. And that was classically proved by Van den Dries and Miller. So I'm going to end this off by proving something non-trivial using O-minimality for you, and you'll see that it's not that bad. There's a very nice way of working with it, I'll tell you, and hopefully people will be happy. Okay, so I'm going to tell you the first non-trivial theorem. Sorry, I'm going to tell you a black box which makes this definition workable. So from this definition, 10 pages of work, you get this theorem, and then you can start proving things. This theorem is called the uniform boundedness principle. I have a very nice statement. Oh, so we're going to assume that this collection of functions is O-minimal and finite. So I'm going to restrict myself to a finite collection of functions over there, but that's okay because whenever you're working with a particular set, you only have finitely made functions that used to define it. So this isn't actually like a legitimate restriction that is finite. We're going to define the complexity of a formula to be the number of symbols in the formula. We're going to count them left to right. X plus y equals 1. 1, 2, 3, 4, 5, 6, 7. 7 symbols. We're just going to count the number of symbols. And the amazing theorem, which I have rarely seen as surprising of a theorem as this, is that the number of connected components of this set is bounded above by some function of the complexity. So if I write down something with 100 symbols, there's an upper bound to the number of connected components it can have. And now I'm going to prove something non-trivial using this, just right out of the box, and you'll see how this is used. Because actually the theorem as stated, it also seems kind of weird. But when I use it, you'll be like, oh, that's how O-minimality is used in practice. So here's the theorem I'm going to prove, and I'm going to end with this. It will only take one blackboard. So the theorem is, let's say that S is one of these O-minimal things, and it does not contain a line segment, not contain a line segment. So those are the two hypotheses. Then there exists an M such that S contains no arithmetic progression, contains no AP, of length m plus 1. Length m plus 1. So this is a statement about the additive structure of S. S actually is bounded one-dimensional additive structure just as the result of not containing a line segment and being definable in this O-minimal structure. We're going to use this theorem as a black box, and it's going to be really easy to prove. How are we going to prove it? Well, we're actually going to prove a stronger statement that S intersected with any line y plus tv. We're going to show that this is upper bounded by some m, which is independent of y and v. Y and v. We're going to prove a stronger statement, not about arithmetic structure, but literally the number of points of intersection with a line segment. So how am I going to do this? Let n be the number of symbols in phi. We're going to create a new formula, psi. And psi's formula is going to be phi's formula. I'm going to modify this formula by writing the word and then I'm going to write down there exists a t in R such that x1 equals y plus y1 plus tv1 and and xd equals yd plus tvd. So I just exhaustingly wrote down what it means to lie in a line. So in particular, the set of points which make this formula true are those that make S true and which make the line statement true. So this is equal to S intersected this line. Now, what can this set look like? Well, this is a finite union of manifolds inside the line. So it's a union of some points and some line segments. It's a union of points and line segments, but there are no line segments. So in fact, this is finite. In particular, the number of connected components of this is equal to its size. So its size, i.e. the number of connected components, equals the number of connected components, is bounded above by f of the complexity. How complex is this formula? I don't know, n plus 1000d. That should do it. I probably didn't write down 1000d symbols. Call this m, and that's the end of my talk. Yeah, so at this, okay, so, sorry, what was your name? Nick, okay. So Nick asked, where does the Pila-Wilke point counting come into this proof? So using just this fact, so okay, so you prove this fact, and together with this claim, you get this theorem with a worse exponent. You get n to the negative 1 over 2 to the k plus 1. So what you have to do from here is we actually prove something stronger than that the probability is bounded above by this. We actually prove an inverse result, which says that if you concentrate highly on one of these sets, then your set of vectors has really high additive structure, really high low-dimensional additive structure. So using a modification of this result, where we replace n with like the maximum probability of concentrating on a point, we can reduce the problem to the case that all these vectors lie inside a generalized arithmetic progression of length k, or just a generalized arithmetic progression of dimension k. So once you have it inside a generalized arithmetic progression of dimension k, the Pila and Wilke basically developed a whole theory of how O-minimal sets intersect with lattice structures. And this says that the intersection with this lattice structure is actually quite small. Well, not that small, but the intersection with the lattice structure can be covered with very few semi-algebraic sets. Then once we have it covered with semi-algebraic sets, we reduce the problem to semi-algebraic sets, and then we use a theorem that exists in the literature, which basically says that the result is true for semi-algebraic sets. That's the Gaussian lineal conjecture, and it involves this little o in the context. in the exponent. So we need to do like a series of reductions from here to get to the point where we can finally apply an incredibly difficult hammer from Daniel Kane at San Diego in order to get this result. But up to here, everything works inside like GLD of R. Like you could do random walks in matrices, and if you're all right with like this result, then it also works for a random walk in matrices, or like any definable group where the exponential map is in the Pfaffian closure. What? Yeah, so you have to replace that with not containing some structure, which is the analog for matrix. That is what it is.